The effect of concentration on the EMF of a cell. Values that were given for standard electropotentials are always measured under temperature of 298 K, pressure of 100 kilopascals, and concentration of 1 mole per decimeter cubed. Now, according to Le Chatelier, and they are equilibrium, so according to Le Chatelier's principle, if we were to change these conditions, then we would expect to see variation in the values that we receive for how easily they undergo reduction or oxidation. So we can use Le Chatelier's principle again, use it quite a lot in our A-level studies. We're looking at this zinc copper cell again. Remember that the species on the right-hand side undergoes reduction, and the species on the left-hand side of this standard representation undergoes oxidation. So we know that in this reaction, zinc loses electrons to become zinc 2+, and copper 2+ gains electrons to become copper. Our more negative one is on the left-hand side, and our more positive one is on the right-hand side. The left-hand side equation ends up going backwards, the right-hand side equation ends up going forwards. So let's think about the copper half cell. Remembering that the equilibrium we're considering is copper 2+ is in equilibrium with copper. If we were to increase the concentration of copper 2+, then according to Le Chatelier's principle, the equilibrium will shift right to oppose the change, and as a result, we're going to gain more electrons and the value will become more positive. Remember, this value is a measure of how much of this reduction occurs. It's gaining electrons, it will gain more electrons. If you imagine it was here on the right hand side, if it shifts to the right, becomes more positive, then the difference between it and the zinc cell, we can see that the difference now is even bigger than it was before. And so our cell potential will increase. Whereas if we were to decrease the concentration of copper, the equilibrium will shift to the left. It will become less positive. So it will shift to the left here, left of the line it was at before, and it will become less positive. So our value will decrease. We need to be careful and not say that it starts going backwards. It's still going forwards. It's still gaining electrons. It's just going to gain fewer. It's still on the right-hand side of the zinc one. It's still pulling, the electrons are still flowing in this direction towards the copper 2+, just not as far, not as many. Okay, so it shifted left, and the gap between it and the zinc half cell is not as big. Then we're going to look at the zinc half equation. We do need to be very careful with this one because this is the negative one. So the equilibrium we're talking about is the equilibrium that was written like this, with an electropotential of minus 0.76 volts. But remembering that Zn loses electrons in the overall reaction, it goes backwards. But we are talking about this equilibrium that's written as a reduction. So although zinc is being oxidized in this reaction, we are talking about the reduction equilibrium when we're talking about Le Chatelier's principle. So if the Zn2+ is greater, this equilibrium will shift right. So we go from where we are here, we'll shift it right. What that means is the gap between it and copper does get smaller as it decreases. It becomes less negative because if we go right and it's a negative number, the number's going up the number line, so it's less negative. But remember that it's actually losing electrons, and look at what's happened to it. It's shifted right. Remember that the electrons are flowing from left to right, and now it's less. It's going to lose less electrons, or fewer electrons. If we were to decrease the Zn2 plus according to Le Chatelier's, we would shift left. So if we shift this line to the left, shift left, we can see that that gap increases because it becomes more negative. We've gone below 0.76, and it's going to lose more electrons. We're even further. Remember, electrons are flowing in this direction, going to lose more. Once the conditions are no longer 298 K, 100 kilopascals, and 1 mole per decimeter cubed, you can't use the standard search symbol anymore because we aren't at standard states. Now, there's this little extra bit at the bottom of the page here, so we just need to put some context to this. If you get a positive value when you do right-hand side minus left-hand side, the reaction is possible. Electrode potential says yes. According to electrode potentials, this reaction is possible. However, doesn't always happen. Why not? They tell us about equilibrium, but not rate. It might not happen if the activation energy is too high. The rate of reaction is too slow, and so nothing happens in a time frame that we're watching it. Many reactions are not done under the standard conditions, and so although we look at the numbers in the table and we say, oh, it's possible, if we actually weren't under standard conditions, we could affect the electrode potential values. We could make the standard cell potential negative so it doesn't occur. If we've changed the conditions, according to Le Chatelier's principle, we may have made it so that the gap here ends up not being a positive gap, and we end up flipping our reactions over.